Why is the universe so big? We live in an observable universe with 41 decillion cubic light years of space. Each cubic light year measures about 10 trillion kilometers per side. We have 41 with 33 zeros after it of these cubes. And this is only the observable part. The entirety of the universe may be much, much larger still. Why? Since early childhood, we probably all began to notice, compare, and ponder the size of things, especially big things. We want to know who the biggest person in the world is, which was the biggest dinosaur, which is the tallest mountain, or the largest airplane. It is not long before we begin asking and wondering about the sizes of the sea, the earth, the sun, the galaxy, and ultimately the universe. It is fun to imagine the size of a whale or a dinosaur. It is thrilling to climb a tall mountain or enter a huge stadium. It is marvelous and inspiring to gaze at the ocean and its enormity. But for many of us, the size of the universe is where the fun stops. We feel small compared to an elephant, even smaller compared to the vastness of the ocean. But the feeling that pops into mind when pondering the size of the universe is insignificance. Not only is the universe large on a scale that completely dwarfs anything we are familiar with, it also contains a ridiculously large amount of stuff. The scale of things contained in the universe is just as disquieting as the size of the universe. One example, our planet is a huge place for humans. We can take endless journeys, explore a vast offering of natural wonders, discover cities and towns for the duration of our lives, and never run out of new places and experiences. It turns out, however, that Earth is just one of many planets that orbit stars all across the galaxy. The recent profusion of discovery of exoplanets, that is, planets that orbit stars other than the Sun, make it obvious that there are many stars that harbor planets similar to our own. Looking up at the sky on a clear night begins to give us an idea of how many planets there probably are. Simply counting them seems impossible. The stars we see are only a fraction of the total in our galaxy, which are estimated to be about 200 billion. We would have to count 3 stars per second for every second of our entire lifetime, never sleep, and live 100 years to be able to count about 5% of them. But there are a huge number of galaxies out there, perhaps 100 billion, which means that we have only counted 5% of 1 in 100 billion galaxies of stars. If we could speak with the landlord of our home, we might point out with some exasperation that we don't need 41 decillion cubic light years of space. We certainly don't need 1,000,000 billion, or perhaps many, many more times that. We don't need 200 billion stars in our galaxy, nor do we need another 100 billion or so more galaxies. Humans are fine with a medium-sized rocky planet, a moon, a nice yellow star, and if we really are in the mood for exploration and spreading to other stars, well, maybe 1,000 more stars. This would make up a truly vast universe for us, and you could save about 99.99999999999999999% of creation. Let's take a look at why physicists believe some things in the universe are what they are. Physicists have figured out how many things in the universe work. The standard model of particle physics may be used with great accuracy to describe the behavior of particles and make predictions on how they will interact. This model relies on a number of constants with fixed values. If you want to use the standard model to calculate what will happen when an electron and a proton interact, you have to plug in the value of the ratio of the proton to electron mass. That is, how many times more massive a proton at rest is than an electron. The number is approximately 1,836. This is a number which has been discovered through observation. There is no fundamental reason why that we know of that this number is not, instead of 1,836, say 7. The standard model in its current form requires a total of 25 constants. Why does our universe have 25 constants which determine the working of particles physics? Ideally, we think of theories in science answering all the questions as to why things are what they are. If we ask why, say, the sky is blue, we expect, and there is, an explanation based on our knowledge of light and particles. The answer that the sky is blue is because that's just the way it is. In other words, the wavelength which determines the color of the sky is just a number that appears in the rule book of the Earth would be very unsatisfying. Some say that the problem is that we have not uncovered the fundamental underpinning of this standard model. In other words, perhaps there is a theory from which the values of the 25 seemingly arbitrary constants of the standard model can be derived, so that one day someone might figure out a fundamental explanation of quantum physics that produces exactly these numbers. Brian Greene, in his book The Elegant Universe, gives us an exhilarating look at how string theory may be able to do just that, relying only on one number, the Planck constant, as input from which all other constants may be derived. It is, however, not so encouraging to note that the book is now over 2 decades old. String theory is a heatedly controversial proposition, and meanwhile, the number of constants the standard model requires has grown from 19 to the current 25. Aside from describing things at the quantum level, physicists rely on some other constants which also appear to be arbitrary. The strength of gravitational attraction, for example, or the speed of light. Is there a fundamental, as yet unknown theory that produces the value of all the seemingly arbitrary physical constants that our universe may be described with? At this point, it seems that science will never be able to derive all physical constants from fundamental theories. Or, to put it another way, we must accept that some physical constants have no underlying reason to be where they are. They just happen to have these values. As far as we know, the numbers that define the workings of our universe could have different values. If there's no theory from which we can derive all of these constants, have we hit a brick wall using the scientific approach? The universe may behave in ways we can understand and predict, but if the initial design has a series of parameters, in other words, the fundamental constants, which cannot be derived from any of our theories, how do we explain this? If our universe was created by design, the creator or creators may have assigned these values like a cook deciding on quantities of ingredients in her recipe. But if the universe was not created by design, how can we reconcile the idea of parameter values with something that evolved on its own? A very difficult question, but science is anything if not resourceful. To explain the seemingly arbitrary nature of the constants of the universe, we turn to the anthropic principle. This principle tells us that the universe we observe has to be one in which sentient beings such as humans may come to exist. Otherwise, we would not be here to observe it. In other words, if the constants of the universe were not what they are, then we would not be around to observe them. Let's unpack the anthropic principle a bit. First of all, what would happen if some constants were different from the observed values? Physicists have calculated that relatively small, less than 20% changes in many of these constants would alter the basic processes of the universe to such a degree that the stars and galaxies we now see would not have been formed. Sentient beings in this kind of universe possibly would not have evolved, so this different set of constants would have never been observed. The anthropic principle does not tell us why the constants we observe are what they are, but it does tell us that if they were different, we would not be around to observe them. This explanation makes sense, but it does raise further questions. Can the physical constants of our universe be a little different and still allow for stars to exist, rocky planets to form, and sentient life to evolve? If you vary gravitational attraction by, say, 1 in a million, things would be different, but not necessarily so different that sentience could not evolve. The term used is tuning. How finely tuned do the constants of the universe have to be for sentience to exist? There is research on the subject, but obviously no one can say for sure how finely tuned these constants must be to allow for sentient observers. The anthropic principle then has left us with only an answer to why the universal constants can't be very different, not why they can't be a little different. That leaves us with endless variations in our constants, which will probably lead to sentient observers. Among the universal constants which cannot at present be derived from the theory is one which is to a great extent responsible for the size of our universe, namely the cosmological constant. As we know, all the matter of the universe, the stars and dust and galaxies that make it up, tend to pull together due to gravity. After the initial formation of the universe, we would expect it to slowly collapse due to this force. However, there is an extremely small counter to this, which pervades all space and is quantified by the cosmological constant. The cosmological constant is the push to gravity's pull. Could the cosmological constant be different? Even a tiny increase would, in a sense, blow up our universe, making it difficult to imagine that sentience could have a chance. Gravity and the cosmological constant define how the universe evolves, and the universe's size at any given point in time is ultimately determined by these two values. The cosmological constant might be one more of the parameters making up our universe, which vary in some regions, perhaps in parts of the universe which are beyond the observable limit. When I first thought of the title to this video, I actually Googled the question of why the universe is so big. I expected many pages of relevant results, but surprisingly, with the exception of the second result, none of the others were really about the question itself. The only relevant result I got was an article from the IO9 Science and Science Fiction blog on Gizmodo, written by George Dvorsky. And it had input from the physicist and writer Sean Carroll. Carroll, who also mentions the subject in his blog entry, "Why is the universe so damn big?" believes that the anthropic principle has to do with the answer, stating that humans are on an in-between scale, many orders of magnitude larger than the scale of particles, but obviously many orders smaller than the universe. What I understand him to be saying is that sentience requires great complexity, which means it must have lots of constituent parts, or particles, which means sentience could not arise at very small scales. But sentience also requires lots of evolutionary trials, available energy, and building blocks, which precludes a sentient being from being too large or forming in the middle of space. He also makes an interesting observation on the scale of the cosmological constant. The cosmological constant is only appreciable at huge scales. You will never notice a negative pressure permeating space on, say, the distance separating the Earth from the Moon, or the distance to other stars in our galaxy. The cosmological constant is in that sense tiny, but it is appreciable fundamentally when trying to understand how the universe itself is expanding. So in a sense, the scale of the universe is tied to the scale of the cosmological constant. Carroll says, roughly, the answer to why the universe is so big is because the cosmological constant is so small. And he adds, why is the cosmological constant so small? Nobody knows. Are we back to square one? Maybe not. The anthropic principle tells us that the universe can't be too different than it is because we would not be around to observe it. This suggests that it could be radically different but would lack in sentient beings. In other words, these constants can be anything, but when they take on certain values, bingo, observers may evolve to measure them. So how did they come to be with these values? Did the constants evolve? Have other values been tried out in past attempts at creating universes? Or are there many universes with different sets of constants? Imagine an ant with a GPS device which gives her the coordinates of the place where she is to a couple of decimal points. The ant takes a look at the device and observes she is at 40.42 north, 3.70 west. She walks around a bit and finds the numbers do not change. So she figures that these values are constant in her universe. She also realizes that they are linked to the position of the sun's path across the sky. So she knows these numbers are important, and if they were different, say 90 degrees north, she would face long nights, freezing weather, and would not be able to survive. To the ant, 40.42 north, 3.70 west are her universal constants. And she knows they can't be too different because she wouldn't be around to observe them. But they could be somewhat different. But they are not. Why? The ant faces a similar situation to our own pondering of universal constants. Of course, if this smart ant had a more precise GPS device, she would immediately understand that these values do in fact vary, but only by a tiny amount when she walks around. The mystery would be very nicely solved for her. The ant lives in a point on the planet that is hospitable to ants, But what she thought was a universal constant was actually a value assigned to a particular place. Could our universal constants also be simply values which vary slightly as we move around in space over time? Could the universe have produced a continuum of values for these constants, but variations are so tiny in the space we can observe that we haven't noticed? Leonard Susskind, who has done some of the most influential work in physics of our time, including foundational development of string theory, delves into the question of fine-tuning in his book, Universal Constants and the Anthropic Principle. In an interview with him entitled, Is the Universe Fine-Tuned for Life and Mind?, posted on YouTube, he summarizes some of these ideas with great clarity. Susskind explains that the observable universe is only a fraction of the total universe. And there are reasons to believe that the universe may be much, much larger than the part we can observe. The reason we can't observe beyond a certain point is that light has not had time to reach us. He also hints that there are reasons to believe that in other parts of the universe, constants may actually vary. Interestingly, he compares the universal constants to genetic material, which vary from place to place in the universe, forming a fitness landscape similar to the evolutionary fitness landscapes discussed in the 2 former podcasts. Constants are only constant in patches of the universe and vary, perhaps similar to GPS coordinates, as we move. In this universal fitness landscape, only certain, possibly only a small fraction of combinations of constants will lead to sentience. Setting out to answer our initial question, we have discovered that the universe is probably even bigger than we usually consider it to be. But we have also discovered that this might surprisingly be the reason sentience and humans are around to reflect on this. If universal constants are not really constant, as Susskind suggests, they must vary very little from point to point on any but the largest scales. Noticeable differences on scales of, say, our solar system or even our galaxy would probably not allow stars and planets to be formed. So, from the anthropic principle point of view, universal constants must be essentially unvarying on galactic scales, but they also must take on different values at still larger scales so that the right combination for the sentience can arise. This explanation is appealing, not only because it gives us a possible answer to what seems to be an impossible question, but also because I feel it tells us something about ourselves. It implies that sentient beings, like us, do not arise so easily from any mix of physical constants. It took billions of years for us to evolve on our planet. But getting to the mix of physical constants to create our planet might have taken just as many billions or vastly more variations of physical constants. We may, of course, not be unique, but perhaps the recipe for creating beings like us just requires a very big universe. So maybe we should not feel so small and insignificant after all. Maybe if the universe were not so big, we would not fit.